All right. Um, so this asks us to open the distance data from our class survey and just look at dot plots, box plots, and histograms and kind of comment on what we like and what we don't like and what we think is the best or disadvantages and advantages of each. So here's our data. Let's open up a data and statistics page. Click down here to open up the distance data. So there's a dot plot. Looks nice, right? It's got dots. Make it a histogram. So kind of the same, you can see the same stuff, right? I always think of a dot plot as a high resolution, the maximum resolution you can get from a data set. Whereas histograms, depending on how you change, how and if you change your bin settings, kind of gives you a lower resolution picture of the data. And then if we go to a box plot, it's really something different. You could argue that a box plot is actually the lowest resolution data because it really doesn't show any data points in here at all. It does show outliers, and this data set's got a lot of outliers. So we can't have a discussion on the video, obviously, but in the class we'd have a discussion about it. The nice thing about box plots is you can see the IQR and you can see the median. Okay, on these other graphs you can't see that stuff. If I were to ask you distance here again, reset it to the standard. If I were to ask you to comment on the mean or the median or the IQR or standard deviation, you can't tell any of that stuff from a dot plot or a histogram. So it's got really good summary information. However, this has got some other things. Can you see skewness? Can you see shape from all of these? Well, here I can definitely see unimodal skewed right. Histogram, I can do the same. Can you see that from the dot plot? Excuse me. Can you see that from the box plot? Well, you can definitely see skewness, but can you see unimodal, bimodal? In fact, to illustrate that you can't see unimodal and bimodal, let me open up another data set here. Let's take a look at heights. So unimodal, symmetric. Let's look at the box plot. So the box is kind of the middle of the data set. Remember how we'd always circle the middle of the data set and then look at the ends? So these whiskers are the ends of our data. They're about the same length, so approximately symmetric. But unimodal, you can't see that in the box. And to illustrate that, let me make a distribution that is very bimodal. So I'm going to grab some of this data, and I'm, again, corrupting my data set, so I'm not going to want to save this. But there we go. Would you agree that that's about as skewed right as you can possibly? That's skewed right. Or I'm sorry, skewed right. Sorry. This is bimodal. You can see that from the dot plot. If I make a histogram, you can see it from the histogram. Actually, just a few FYI, if you make your boxes too big, sometimes you can't see that even. So a histogram that has really big bins, sometimes you can't see bimodal. It's another disadvantage of that. But you can't see it from the box plot. It's just, it's just a box. Doesn't show any peaks at all. So that's a disadvantage of the box plot. So don't comment on unimodal. If I give you a graph of a box plot and ask for shape, just comment on skewness and symmetry. All right. So here's some graphs where I give you the histograms, the dot plots, and the box plots. And I guess I should have commented on those things I just talked about looking at these. As you can see, bimodal, can't see it here. Unimodal, can't see it here. But you can see symmetry. Look at the tails. You circle the middle, look at the tails. 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 Okay, so there we go. So here's some fictional test scores comparing football players' performance on a test to hockey players. This is completely made up. But the nice thing about box plots, actually, I think if what I've heard about the history of these things is correct, box plots were made for comparing distributions. It's like their main purpose. So this is where they really shine. In fact, if I didn't have this summary information, I could compare these distributions pretty easy. I could say the median of this one is bigger than the median of that one, and I can actually approximate them, 86, 70, 63. I could say the spread of this one is less than the spread of this one, and I could come up with approximations for those. And I could look at the shape, and I could get a really good comparison just by looking at the graphs. Okay? So we are going to compare with CUS, with context. Make sure you use comparison words. But I actually have a lot of information. So here's the means, here's the standard deviations, here's the medians, and if I subtract these two, I can get the IQRs. Okay? And I can see the graphs. So comparisons, center. So football players obviously had, their test scores were centered at higher spot than the hockey. So what value should I comment on? Should I comment on the median or should I comment on the mean? Does it matter? Well, you can comment on whichever one you want. But I see this as being skewed to the right, and this is an outlier. So those two values, or those two ideas, or those things are going to kind of influence these mean values. So I'm going to comment on the median because I think it's a better measure of center. The scores. The median score for football players, and I'll cite it, 85.5 is greater than the median for hockey. And that was 68.0. I have my comparison word? Yep. Spread. This one is less spread out. This one is more spread out. So I'm going to cut some corners here. I probably wouldn't recommend this on the AP test, but I use context. So I kind of already got my context box checked off. And the other question is, do you really need to put these specific values down? Or can you just say the median is higher? Well, you never know what they're looking for, but usually you don't need the values. So I'm going to cut some corners here. I'm going to say IQR for football is less than IQR for hockey. Not much detail there. Kind of running a risk maybe, but I think it'd be okay. Shape. Football. So football is, so what are we going to say here? What about the symmetry or skewness? And if you look at these whiskers, you're going to say, oh, that's symmetric, but it does have an outlier. The nice thing about these outliers is you can visualize the whisker with and without the outlier. So this distribution is skewed left, period. Now, if you wanted to omit the outlier, it's approximately symmetric. So you could say approximately symmetric if you omit the outlier, but you really have to say you're going to omit if you omit the outlier. You gotta. So this response by itself would actually be pretty good. This response by itself is good, or both is better. Just don't say it's skewed. Don't say it's approximately symmetric, and just not say you're omitting that outlier. Hockey, skewed right. Notice I'm not commenting on unimodal, bimodal, because I can't. Outliers, unusual features. I think this is one value. You got to be a little bit careful about that because there could actually be two values there. So it looks like there was one football player with an unusually low score. Well, not a low score relative to hockey, but low score relative to football. No outliers in the hockey data set. Okay. All right, there we go. Matching exercise. I guess I would just challenge you guys to pause the video and do your matching, I guess. I'm going to just do it quickly here. So like I said, pause the video. I'm going to do it real quick. First thing I would notice is that this distribution is skewed right, and these are all kind of symmetric. And there's only one box plot that's skewed right, so that is absolutely B. Now these next ones, if you know, a lot of times kids are looking at outliers or stuff like that, but just look at the spread. This one is the most spread out. This one is next. This one is a little less, and this one is the tightest. You should be able to get that from the widths of those boxes easily. Biggest IQR box, D. Middle one, these two are pretty close. This one's definitely bigger. C. A. Done deal. All right. This last page really is just some summary stuff about standard deviation. The units of standard deviation are the same as the units of the original data set. Standard deviation is never negative. The formula's got the square root in it, positive square root, so it's always positive. Plus, you're taking those deviations and you're squaring them. So it'll never be negative. Remember, standard deviation is a measure of spread, or more specifically, the measure of the average distance from the data points are from the mean. What would it mean for the standard deviation of a data set to be 0? It has no spread. Well, that would be every single data point has exactly the same value. So it is possible to have a 0 standard deviation, just not very likely. Variance is a standard deviation squared, and the units of variance are the square of the original units. And then here are some notational things and a refresher of the formulas, I guess. There was a lot of students didn't do well on the symbols in the last test, so I'm going to hit it again. X bar, sample mean. Mu, population mean. S, sample standard deviation, sigma population, variance S squared, sigma squared. And then these actually don't have special symbols or stuff like that. So kind of tells you how important these are relative to these also. So, right, that's the end of chapter 1. Good luck prepping for doing your homework and getting ready for the next test. The content is certainly easier than the first chapter, than chapter 4, but still need to prepare for the test.